All right, let's get started today. Remember yesterday we had this little conundrum. Um, if we have Alec, right, standing by the sidewalk and Brittany's doing a little jog, right, and she's carrying some charge. Let's call that charge C, right, some charge C, right. What happened is that, in this case, right, Alec will observe that there's a charge moving in a magnetic field, right? If we use our little right hand thing, right, we figure out that there's going to be a force on this charge, a magnetic force on this charge that's going to be kind of lifting it up, right? You have a little levitation situation. But if we move to, move our go cam over to Brittany's head, right? She is not moving, right, in her own frame. So therefore now the charge is not moving, and therefore there's actually no magnetic force somehow, right? This charge C. Okay. So have you guys figured out how to resolve this conundrum? Did someone read ahead and figure it out? Okay. So if you read ahead, don't give it away. Well, you could give it away. It's not like a big mystery or anything like that. Okay. And so this has to do with reference frames. Okay. And this is something we cover if you were here last semester with me. We covered it in chapter 4, and then we just stopped talking about it. Okay, so unfortunately, this is stuff that, remember like 8 months ago? We talked about this for a couple of days, and now you have to remember it, right? But so let's let's get a little refresher on what a reference frame is. Okay, so let's say we have two people, okay, Alec and Brittany, right? One is moving relative to another, okay? And the way we denote that is that, well, Brittany is going to be moving in Alec's frame at some velocity VBA. Does that make sense, the notation? Right, this is the person that's moving, and this is the reference frame we're looking at, okay? Okay, so if Alec is sitting still on the sidewalk, Brittany is running along the street, right, then VBA denotes basically what her velocity is in the sidewalks or Alex's frame, but it's also denoting the how the two reference frames are moving relative to each other. Okay, so we're going to start using this stuff called relativity. Not quite the Einstein relativity, but this is going to get us towards that if you're interested. Okay, and let's say we have some particle, I don't know, let's not call it a charge, right? What starts with a C? A cat, right? That's running along in both these frames, right? Right. Let's say we figure out how fast the cat is running, in Brittany's frame, right? Okay. And we want to figure out how fast the cat is running in Alex's frame. The way we do this is we basically add these two vectors together, right? The example I usually give when we're doing chapter 4 is that, well, if we have a person on the sidewalk and then we have a train that's going by, right? Let's say the velocity of this train is 5 meters per second or something like that. And you have a person that's also walking inside the train, right? So this will be velocity of the person in train, right? Let's say, she's going at 2 meters per second, right? From someone sitting on the sidewalk, right, it will look like that person is actually walking at 7 meters per second, right? Because both the train speed and the person inside the train speed adds, right? So hopefully that makes sense, right? So you want to convert one velocity from one reference frame to another, you just add those velocities, right? You have to figure out what A's and B's and C's are, but a lot of time the concept is just that you have to add them sometimes, right? Okay. So the thing we're dealing with up here, right, is that there seems to be some conflict between what is the force in one reference frame, what is the force in another reference frame, right? Somehow there's forces in one reference frame but not another. Okay, so in order to go from velocity to forces, right, we'll pull out our little calculus tools, right? And figure out, well, if we take a derivative of both sides of these equation, right? We can do that with in math, right? We end up with acceleration instead, right? If we end up with acceleration instead, what happened is that, well, we're going to take this special case where the two reference frames are going at a constant velocity with each other, okay? We're not going to accelerate. The train is not going to accelerate. It's just going at a constant 5 meters per second. In this special case, what happened is that the time derivative of the velocity vector between the two reference frames, maybe A and B, right? Alec and Brittany, right? This term is actually equal to 0, right? Because if we're having a constant velocity, right, the acceleration has to be 0, right? So therefore, we can actually find that, well, the acceleration that someone would observe the cat will have by Alec and the acceleration of the cat in Brittany's frame, they should be equal to each other, right? Because the two frames are not accelerating with each other, because this term just went away, right? So if you multiply both sides by m, you end up with force, right? So mass times acceleration is the force. So therefore, you would think that, well, the force in this case, I'm going to flip back and forth between the cat and the charge, right? The force that the charge will have in Alex's frame should be exactly equal to the force on the charge in Brittany's frame, right? So now we're back into the same problem, right? It seems like the two reference frames should have the same forces, right? But why is there one that has a magnetic force, the other one doesn't? Okay. So those of you who read ahead, or actually anyone who did not read ahead, like, so how do we resolve this problem? Anyone want to venture a guess? Anyone who read ahead and then want to tell us what the answer is? Yeah, the magnetic force is relative to the movement of the charge in that reference frame, right? So in Alex's frame, the charge is moving, but in Brittany's frame, the charge is not moving, right? Because she's just holding it in front of her, right? Okay. There's something more than the magnetic field. What is the other field we've been talking about? Electric field, right? So somehow, right, just by changing from one reference frame to another, right, somehow we're actually able to create electric field. And this is known as the transformation between electric and magnetic field. So maybe my scrolling already gave it away, okay? So let's go through this little thought experiment once again, right? I'm going to redraw it. I should have just copied and pasted it, right? We have, let's do this in Alex's frame, right, where Brittany, right, is carrying this charge, right, running along at some velocity v, and we're going to call that v velocity of Brittany in Alex's frame. Okay, we're going to be more specific. Okay, right. In this case, right, there's going to be, we already did our little right hand rule. We're going to see that, well, there's some force going to be lifting this charge up, right? So in Brittany's point of view, right, so this is, let's call this A frame. Okay, this is going to be called B frame. Okay, in Brittany's point of view, right, she is running in her own place, but then the charge is not moving relative to her, right? Okay, but Alec is the one that's actually moving. In fact, Alec is actually moving backward with velocity negative VBA, right? Because you can tell that, if you relative to each other. Okay. So what happened is that, well, there has to be a force that's being exerted on this charge, right? And since the charge is not moving, the only thing we have left is actually the electric field. So there has to be some sort of electric field that's going to be exactly the same as the magnetic field, because Brittany will also feel the same levitation on that charge. Okay? So in fact, we can equate these two. Okay? That means the force that is seen, the magnetic force that is seen in Alex's frame has to be equal to the electric force that is seen in Brittany's frame. Okay? And calculating the magnetic force, let's just do this in the next line, right? It's just the charge times the velocity. In this case, it's going to be VBA, right? That's how fast the charge is moving. Cross-producted with the magnetic field, okay? And this magnetic field, right, is observed in Alex's frame, right? Okay, so that has to equal to whatever the charge is times the electric field that is being observed by Brittany in Brittany's frame, okay? In fact, since they are the same charge, these will actually go away. So we actually have a way to calculate what is the electric field that gets created, right, in Brittany's frame, right, due to a charge that is moving in a magnetic field in Alex's frame. Okay? Okay. So in this little experiment, it shows that if you are moving in a magnetic field, it actually creates an electric field. Right? It's a little weird, right? Because right now, right, before this, right, we're talking about electric field separately, magnetic field. We did do a little bit of induction, right, where, you know, a changing magnetic field creates an electric field. But we haven't, like, shown that, you know, they actually can turn into one or the other depending on your frame of reference. Okay? So we can, you know, this formula, I'm just copying it down. Okay? So in general, right, there could be an electric field that exists in Alex's frame already, right? In general, there could be, right? We don't know that, right? So in order to calculate the total electric field in Brittany's frame, not only do we have to have this factor, right? But we also have to add whatever it already existed in Alex's frame, right? So this is the first formula we're going to use to calculate the electric field from Brittany's point of view if we have an electric field in Alex's point of view, and also a magnetic field in Alex's point of view. So we measure these things in a frame, but then we can actually predict what it looks like in someone else's frame of reference. So let's do an example quick just to solidify this. Okay, so we have some laboratory that created a parallel electric and magnetic field. Okay, the electric field strength is 10,000 volts per meter in the I hat direction, so along the x direction. The magnetic field is only 0.1 Tesla. Okay, a proton is shot into these fields, right, with velocity 1 times 10 to the 5 meters per second in the y hat direction, in j hat. Okay, what is the electric field in the proton's reference frame? Okay, so I'm going to try to draw this. So it's the setup part, right, where we have, I'm going to set my x and y axis, right, y, x, okay, and then both the electric field and the magnetic field are in the x direction, so we have an E field that is 10,000, right, in the I hat. I'll leave the units off, and then we have a magnetic field, right, that's 0.1 Tesla in the I hat direction also. Okay, the proton is shot vertically, right, in the y hat direction. So let's just have this going straight up. So V of the proton. Okay, we're going to have to assign, like, subscript A's and B's to this, right? Because in order to use this formula, we have to know what is subscript A, what is subscript B, what is subscript BA also, right? Okay, so what we're going to do, so we're going to call this the A frame. Oops, not A hat frame, right? We're going to have to translate this over to the proton's frame. Okay, so this is what is observed in the lab. This is from the proton's point of view. So now we're going to put the little go cam on the proton. Okay, and what happened is that, right, it also has these coordinates, and a lot of times if you are taking relativity, this is actually going to be marked prime, but it's just superficial at this point. Okay. So what happened is that there's going to be a different electric field in here, and we don't know what that is. Okay. So what we're going to do is we're trying to figure out the electric field, right? So what we're going to do is we're going to use this little equation that we just found above, right? The electric field in the B's frame is the electric field in A's frame plus the velocity between the two frames cross producted with the magnetic field in the B frame. There's no factor in front, right? Yeah. Okay. So before even drawing the electric field, I'm going to try to figure out what the direction is, because there's already an electric field, right? That's EA. We're going to have to add this vectorially to this VB cross BA, right? So the velocity of B, meaning the proton in A's frame, right? So that's how you interpret this. The velocity of the proton in the lab frame, right, is in the positive j hat direction, right? So I'm going to do my 1, 2, 3 rule once again. So when I do a cross product, I do 1. I cross it with the magnetic field vector, right, which is going on to the left to me and right to you. Okay, go in this direction. Okay, and then my thumb is going to point in the direction of what the cross product resultant is going to be. So it's actually going to go into the board, right? So what's going to happen is that the electric field, right, is going to be going, the original electric field is going to be like this, but then you're going to add some electric field going into the board, okay? Let's just call it E plus, right? This is actually going to be VBA cross BA, right? That's what that is, okay? Right? So let's figure out what that magnitude is, because we already figured out what the direction is, right? So the resultant electric field in B's frame is going to be whatever it is in A's frame already. It's 10,000 in the I hat direction. And we're going to add to that, okay, V cross BA. And we're going to know that since this is a XYZ coordinate, right, so Z is coming out, right, so whatever direction it comes out to be is going to be in the negative K hat direction, right, because it's going into the board, okay? So we're going to take the velocity of the proton, 1 times 10 to the 5. Oops, I need more space, right? 10 to the 5, not 10 times 5. Okay. Multiply by whatever the magnetic field strength is, which is 0.1 Tesla. And all of this, since they're perpendicular to each other, we don't have to, the sine of the 90 degrees will give us a factor of 1. Okay. And this is going to be in the negative K hat direction. Okay. So it's going to be equal to 10,000 I hat in volts per meter plus, well, I'm going to pull this negative sign and put it in front, negative 1.0 times 10 to the 4 in the K hat direction volts per meter. Okay? Okay. So that's how you figure it out. What is the electric field in the proton's point of view? Okay? So interestingly, so 1 times 10 to the 4 is actually 10,000, right? So it's, when you do this transformation, right, what happened is that the original magnetic field magnitude is actually almost, it could be the same as the electric field that's actually created just by changing from one reference frame to another. And you're going to see this in the worksheet today when we work on that. Okay? Okay. So that's how you transform, right? That's how you figure out what is the electric field from one reference frame to another, okay, if you have a magnetic field in reference frame in the first place. You can also do the same thing with magnetic fields. So the magnetic field also changes going from one reference frame to another. I'm going to do this a little bit quicker because I just don't want to spend the entire lecture on it, because the math gets a little bit funkier because we're going to have to deal with magnetic field instead of electric field. So I'm going to just go through this real quick. Okay. So what we're going to do is we're going to think about, well, let's start with a charge that is not moving, right, in frame A, or another word, Alex's frame, the one on the sidewalk. Okay. And frame B is moving, right? Just as usual, where Brittany is running along the street. So let's say we have Alec. Now Alec is going to be holding the charge, right? Some charge C, okay? And it's not moving, but then Brittany, right, is once again running along with velocity VBA, okay? So this is in the A frame, okay? So in this case, right, there's no charges moving, right? So therefore, there's no magnetic field, right? Okay. What we're going to do, let's see, okay? But what's going to happen is that since you have a charge, right, you're going to create an electric field that's coming out like this, right? Remember, a point charge will create an electric field that's radially outward, okay? So if we go to Brittany's frame, okay, let's cut this off, okay? But what Brittany's going to see is that there's going to be an electric field in Alex's frame, okay? And there's also going to be a charge in Alex's frame that's moving, right? So in Brittany's frame, what happened is that she is standing still, and then Alec, right, is the one that's moving backward, negative VBA, with some charge C, right? Okay? So you can actually calculate exactly what that is. So since you have a charge moving, right, in your reference frame, right, and there's also an electric field here, right, let's create it, okay. If you have a charge that's moving in your reference frame, that means you can actually apply the Biot-Savart's law that we learned about chapter 29, right? So the Biot-Savart's law, just to remind you what it looks like, actually chapter 28, was it? No, I think it's 29, right? In order to calculate the magnetic field, right, you take the cross product of the velocity with the r hat direction, right? And then it's proportional to this mu naught, this constant, over 4 pi, the charge divided by r squared, okay? Right? So in this case, right, we're not interested in the charge, the speed of the charge in Brittany's frame. We actually have to have the charge, we're actually going to convert that to how fast is Brittany moving in Alex's frame, okay? In that case, okay, remember that the speed that Brittany is moving in Alex's frame is actually negative VBA, okay? And therefore, that's what this negative sign up here comes from, okay? And we're going to massage this a little bit, okay? And what happened is that when you do this massage, so don't worry, you don't have to like know how, I mean, you can read how it's done, but it's like a particular method in order to just get the equation that we want, okay? So once we start with this negative sign in front, we can kind of like group things in a special way, okay? What we're going to do is we're going to take this charge and put it at the end here, put this r hat, put it at the end, and then put this 4 pi, put it over here. Maybe you guys are seeing what I'm trying to do here, right? Because the stuff over here looks like something, right? Okay. What I'm going to do is also multiply the top by epsilon naught, divide by epsilon naught, so that's just the same thing as multiplying by 1, and put this epsilon over here, right? And what does this look like to you guys? The electric field from a point charge, right? So therefore, right, this complicated function stuff in front cross producted with the electric field, right, of a point charge, which is going to be whatever the electric field measured by Alex's frame, okay, that's going to create a magnetic field in Brittany's frame, okay? All right, everybody's head is, you need more coffee to figure this out, right? But what's interesting about this is that, so the same thing happens with electric field and magnetic field, where if you have an electric field in Alex's frame, right, but then Brittany is looking at you moving, it actually also creates a magnetic field, right, not just an electric field. Okay, so that's the other equation that we're going to be using. And before we use this equation, notice that there's this epsilon naught, mu naught thing multiplied together, right? They're both this weird constants, right? The epsilon naught come from Coulomb's law, right? That's when we first saw it, right? Where did we first saw mu naught? You guys remember? I'm sorry? Yeah, magnetism. This is the part that's come from the Biot-Savart's law, right? Right? So this has to do with electric field. This has to do with magnetic fields or their forces. And what's really funky about it, if you take those two numbers, divide, take the reciprocal of it and take the square root of it, you get exactly the speed of light in a vacuum. Okay? And this is how this electric field and magnetic field stuff gets connected to light, which is the stuff we've been seeing all this time. Okay? Right? So to you guys, right, because you guys grew up in the 21st century, right, it may not be a surprise to you that electricity and magnetism is connected to light, because you probably heard of this thing called electromagnetic field all your life. But imagine this, in the 1800s, when people don't even have light bulbs, right? There's just, they have these little chemical battery that generates current for them, right? And it does some stuff, and somehow it also creates a magnetic field. And they have a bunch of, permanent magnet they find, from rocks, right? And they say, oh, well, this, like, they stick together somehow, right? All of this kind of somehow combined together to make, what light is. And this is a huge surprise to, people back in the 1800s. Okay, but just to wrap up before we go to the worksheet, so these transformation equations are called Galilean, meaning like Galileo, even though he wasn't around back then. These are called Galilean field transformation equations, and they're just written here. Okay, where if you want to figure out the electric field in Brittany's frame, you need the electric field in Alex's frame, but then you also have to add to that the cross product between the velocity of the two frame and whatever magnetic field is inside Alex's frame. Okay. Similarly, if you want to figure out the magnetic field in Brittany's frame, there's going to be this 1 over minus 1 over c squared, and that's because, remember, that if you square this, right, c squared is actually equal to epsilon over mu naught, and therefore 1 over c squared is actually epsilon over mu naught, which is exactly what's in this formula up here, right? And there's a minus sign also in front of it. Okay, so therefore that's where that comes from. Okay, and you have to do this cross product thing once again. Okay, let's not do the stop to think. And before we jump into the worksheet today, I just want to give you guys at least 20 minutes to do it. This is basically what was the foundation for Albert Einstein to come up with this thing called on the electrodynamics of moving bodies. And it's actually a paper that's been translated to English, and those of you who are interested in reading it, it's actually very readable for everyone in this class. So you can actually understand the original writing of Albert Einstein when he published his paper in 1902 on special relativity. Okay? Okay, any questions? Well, I transfer over to